Before we get into some of the skills and the topics related to electromagnetic radiation, I first want to point out that a lot of the problems we're going to refer to electromagnetic radiation as either light or as the particle photon. So it's just important to point out that we can use these all pretty much interchangeably. We can think about it as an electromagnetic wave or as a photon particle. So a lot of the problems we'll use these interchangeably, and just don't get confused. They're all equivalent for the sake of these problems. So the first skill we're going to need is to use these two equations in front of us. They're pretty simple in the math. So here for this first one, we have nu, which is the frequency. We have c, which is the speed of light in a vacuum. And then we also have lambda, which is the wavelength. And it's also I think it's important to point out that typically your wavelength is going to be in nanometers. That's typically what we're going to measure it in. But our C is usually in meters per second. So then our nanometers and meters wouldn't cancel. So a lot of times you have to use this conversion. You want to convert your wavelength into meters through that so that your length measurements cancel out. It's a common room for error. And then we also have this one on the right here where we can map energy to also frequency, where h is the Planck's constant. And then nu, once again, is just the frequency. And you can also plug in, I could also write this as E equals Planck's constant times c over lambda. If I wanted to just sub this equation in, you can do that. So let's look at some quick math problems. These ones aren't too bad. 7. Calculate the wavelength in nanometers of light that has a frequency of that many reciprocal seconds. So we know we want a wavelength, and we are given a frequency, and we know that the relationship between the two is nu equals the speed of light over lambda, where nu is our frequency, and then lambda is our wavelength, and c equals 3.00 times 10 to the 8th meters per second. And we are given a frequency, and we want to solve for wavelength. So if I just solve this equation for wavelength, I get, that was an arrow, I get the wavelength equals c over frequency, and I can just plug stuff in. 3.00 times 10 to the 8th meters per second over the frequency, which is 4.62 times 10 to the 14th reciprocal seconds. These seconds cancel. If I throw this in our calculator, oh, my battery's low. We will get 6.49, we'll call it 4 times 10 to the negative 7th. And this is, we have meters here, so this is going to be in meters. But the answer they want is in nanometers. And so if we know that there are, answers. We know that there are 1 times 10 to the 9th nanometers in 1 meter. So if we, let me move this is getting messy. I know that unit conversion exists. So if I take 1 meter and then 1 times 10 to the 9th nanometers, my meters would cancel and I would get nanometers. So I need to take the answer from previously and times it by 1 times 10 to the 9th, or just 10 to the 9th. And I get, as my final answer, I get 649.4 nanometers. Okay, which looks like C. Okay, I moved the question down a bit because it was getting cramped. 10. Calculate the energy in kilojoules per mole of 1 mole of green photons, and they tell us the wavelength of a green photon. So we know the equation for energy of light is E equals Planck's constant times frequency, which is the same as Planck's constant times the speed of light over wavelength. So we're going to want to use this one here because obviously they tell us wavelength. So let's first, what are our constants? C is 3.00 times 10 to the 8th meters per second. Also, the reason I round it to 3 every time to 3 sig figs is probably pretty arbitrary, just out of habit. But anyways, our wavelength is 525 nanometers, which is 525 times 10 to the negative 9th meters, if we convert that. And then our Planck's constant is 6.626 times 10 to the negative 34 joules times second. So if we start plugging stuff in, E equals 6.626 times 10 to the negative 34 joules times second. Speed of light is 3.00 times 10 to the 8th meters per second. And this is all over our wavelength, which is 525 times 10. It's a horrible X. I'm redoing it. Times 10 to the negative 9th meters. Let's look what's going to happen to our units. This seconds is going to go on the bottom, which will cancel with that seconds. And our meters cancel, so we will have joules. Okay. 6.626 times 10 to the negative 34 times the speed of light divided by our wavelength in meters. And I get that the energy is 3.8-ish times 10 to the negative 19, and this is joules. Now, important note, to solve this problem, you need to know that this energy that we did is mapping per 1 photon. So this energy here is essentially a joule per 1 photon. And they want the energy of an entire mole. So let's convert from 1 photon into 1 mole. What's our conversion there? It's going to be Avogadro's number, because there is an Avogadro's number of particles in 1 mole. So I'm going to want moles on the denominator, and then I'm going to want Avogadro's number in the numerator, because I know there's that many photons in 1 mole. So let's multiply our previous answer by Avogadro's number. And I get, so this is now, let's see, this is now 228,000 joules per mole. If I divide this by 1,000, I get 228 kilojoules in 1 mole. So, and that's E. So next you're going to need to know the electromagnetic spectrum. I'm not going to write all that out, but that's what we're looking at here. And for different wavelengths, we have different types of electromagnetic radiation or light or photons. So for this very specific wavelength, we have the visible region, which is what we can see with our eyes, and it still exists outside of that region, and you get the different types. It's also worth mapping one thing, is that we know energy is proportional to frequency. So as our frequency as our frequency increases in this direction, so is our energy. So up in this region, we are high energy, and down here we are low. That's one important point, that a lot of times when they ask you the specific spectrum questions, they are going to ask you in the context of which ones have high or low energy, which we'll take a look at in a second. But there's not too much here to explain other than you kind of just got to know this and know the different regions. So here we can take a look at a question which kind of goes off what I was just saying. So here you literally just kind of need to know the spectrum. So as I said before, roughly, if I draw up like a rough one, if we say this is like the visible region, viz, IR is to the right, infrared, and this is UV. I think these three are the easiest to remember because we know the this is one little trick that might help you, is we know the visible spectrum follows a rainbow, right? It goes blue, like green, yellow, orange, red, and it goes in this order. And we know, purple is gonna be on this side. That's, UV is called ultraviolet, so it's gonna be on the purple side, and IR is gonna be on the right side over here. And also, microwave is to the right of IR. And I also know that energy, that's an arrow, energy trends this way. So even if I don't know the entire spectrum, if I just know kind of the easier to remember ones, if you know visible is in the middle, UV is to the left, IR is to the right, and microwave is to the right of IR. Let's see if we can still get this one right. So I know E has to then be correct. So even if I know nothing about the rest of this spectrum, I could still perhaps piece it together just by the fact that I know the order of the rainbow. So we keep describing electrons and where they fall around an atom. Let's formalize the way we can describe where an electron is. So for this, we're going to introduce the quantum numbers. Electrons first, we can classify them arranging into shells. And within shells, we have subshells. And within these subshells, we can have orbitals. So when I say shells, I am talking about the energy levels. This is the most broad category, and this is like what we were talking about earlier. You can have an electron in the first energy level, the third, etc. You can also have different types of subshells, and these are the types of orbitals. Orbitals. I was doing green. I don't know why I just switched to blue. Types of orbitals. And when I say this, I am referring to either S, P, D, or F. Also G. I'll erase that. That's not important. And so yeah, we can see down here in this picture, you can have the S orbital, which is more of a circle, or the P-type orbital. And furthermore, we can also we're going to want a way to describe which specific orbital it is. So in S, there's only one S orbital, but for P, there are 3 for each energy level. So we're going to want a way to describe which of the 3 is it. So then I'm going to describe this as which specific orbital. So for P specifically, since we have 3 of them, we can classify the 3 as -1, 0, and 1. And I'll formalize this more in a second, but so then this introduces then our 3 classes for the quantum numbers and classifying our electrons. So what are the actual quantum numbers? Well, we have N for the energy level, and then we have L for the type of the orbital, and then M for naming which specific orbital it is. And these 3 quantum numbers can then describe any orbital we want to describe. And let's see. Okay. And you just say them in that order. N can take any number of which energy level we're in. L starts from 0 to 1, so I don't know why I erased that. L, S is going to be equal to the 0L, P is equal to 1, D is equal to 2, and then F is equal to 3. And then M, we know that you add 2 more orbitals for each. Every time you go down this direction, you add 2 more orbitals. So S has 1 orbital, P has 3, D has 5, and F has 6. So let me create a graph like this. Okay, so for S, and this is the M quantum number. Let me move this down, actually. Okay, for S, the M numbers it could take are 0. So there's only 1, and then P can take -1, 0, or 1. D, we know it has 5, so it can take -2, -1, 0, 1, or 2. And then F can take -3, -2, -1, etc., etc. And this kind of makes sense because we know how many electrons each one of these can hold. We know an s orbital can only hold 2 electrons. So it makes sense that there's only 1 orbital. And the p orbital can hold 6 electrons. We know D can hold 10. We know F can hold 14. So I think it's kind of intuitive to think about it this way. And we're just going to give them any arbitrary number we want to describe which orbital it is. Okay, so let's take a look at a question. What are the proper NL values and the number of orbitals for the sublevel 2p? So when we write it like this, 2p, 2 is the energy level, and then p is the type of orbital. And so we know the energy level, we know this is going to map N, and so that equals 2, and then the type maps L, and for P we know that's 1, so then I know it's 2, 1, which eliminates this answer, and that answer. And they want to know how many orbitals are in the 2p. I know that P has, it has 3 orbitals. B. Which one of the following orbitals is represented by the radial probability distribution plot pictured below? So the first thing about these questions is they put on the graph the N and L energy level. So immediately I know that the N is 3 and that L is 0, which corresponds to S. So immediately I know it's 3S without even reading the graph. And I'm not sure if you're supposed to know how to actually read these. These are in the book. But just to point me off, I know there are 2 nodes, and that for the s orbitals, you will always have, n minus 1 number of nodes. So if you have 2 nodes, I know I'm in the 3rd energy level. But perhaps you don't need to know this, and you just read the quantum numbers.